Hello and welcome to episode 15 of Probability and Statistics for Engineers, and I am Mohammad Momedzadeh, the presenter of this lecture. So today we want to talk about several topics. Indeed, in this lecture, we will discuss about the discrete probability distributions, some familiar forms of the distribution will be discussed, and we will discuss about the uniform distribution and binomial distribution as well. So the observations generated by different statistical experiments have the same general type of behavior. Discrete random variable associated with these experiments can be described by essentially the same probability distribution and therefore can be presented by a single formula. The following are the probability distribution that will be covered in this chapter. So the discrete, uniform distribution and binomial distribution will be discussed in this chapter. Later on we will discuss about the multinomial distribution, hypergeometric, geometric and Poisson distribution and process. So it's important to understand the concept of this chapter and the discussion that we have it for the remainder of the semester. So it's important to understand that mainly we recognize the environment by our similarity with the different experiments. What do I mean? The artificial intelligence working like this. I mean, you will look at 1, 2, 3, 4 cats, and later on, if you just look at the cats, you can recognize that animal as a cat. So this can be happen because of the experiment. Means that as much as you get an experiment, you can distinguish between the cats and other animals better than the others. So we do the same thing over here. We will discuss about some type of the discrete distribution. We will talk about the distinguishable characterization of these distributions, and by finding that type of the characterization in any process or a statistical experiment, you can use this type of the distributions. I mean, for instance, the most applicable distribution that we have it in a normal life in a discrete cases is a binomial distribution. You will see that this binomial distribution can be seen in anywhere in around of us. So by finding that character in some statistical experiment, easily you can somehow diagnose that type of the distribution in that statistical experiment and use that type of the distribution to solve that probability. Instead of calculating the probability by a lot of difficulty, you can use that formula, or you can use that general format of the formula, then you can solve that probability as well. So let us take a look at each of these distribution one by one, and let us discuss about them. We will start our discussion by the simplest one, which is a uniform distribution. So let us take a look at the discrete uniform distribution precisely. The definition said that if the random variable x assumes the value x1 up to x4 with equal probabilities, that's the key over here, that the probability of occurring or appearing x1 up to xk are equal. So then the discrete uniform distribution is given by 1 over k for any outcomes. So it's important to mention about these things that normally in a real life it cannot be seen that all the elements has the equal probabilities. For instance, consider one bag that contains some balls inside of it. So for example, we have the blue balls, the different color balls over there, the blue balls, the purple balls, or the different balls inside of it. So and assign a numerical value for each color. For example, put a number over here for each. For example, 1 for the blue color, 2 for the purple, 3 for the orange colors. So then one person put his hand inside of that bag. Let me just sketch a hand. It's not normally looks like a hand, and choose one ball unseen and take it out from the bag. Then the probability of getting each of these actually balls has a same probability, equal probability. They have the same likelihood to be appear, to be drawn from that type of bag. So right now, if I want to sketch the probability distribution function and denote the colors by the random variable, means that x equal to xi can be described by 1, 2, and 3, then the probability of appearing 1 or the blue color will be 1 over 3. The probability of appearing number 2 or a purple color is 1 over 3, and the third number is 1 over 3 as well. So as you can see, we have 3 objects, and the possibility of getting each of them has a same likelihood. So because of that, the probability of getting 1, 2, 3 are the same, and this probability is actually divided by these objects, and the probability will be 1 over k, because we have k objects, 3 objects over here, and we can calculate the probability easily. So for a die, if we flip a die and the probability of occurring that numbers are the same, means that the die is fair, it's unbiased. It's not actually modified such a way that some number appear more than the others. Then we have a uniform distribution for selecting each of these numbers, and if I select the xi as a appearing number, then the probability will be 1 over 6, because we have 6 objects over here. So it's easily can be seen that if we have this type of the distribution, for example, if I just use that table of a distribution for the uniform distribution function, then at the first line I have x equal to xi, and the numbers that can be appear is listed at the first line, means that it will be x1, x2, x3 up to xk, and the probability for each of them is 1 over k. So if I want to calculate the expected value, simply you remember the formula for the expected value. So means that the mu of x, or expected value of x, will be the summation. Because it's a discrete distribution, we should use the summation. It should be equal to the summation of a probability by the the random variables, means that xi multiplied by the probability of that one, the function that we have, it 1 over k. So the k is not related to that value, so we can take it out, and the mu will be like this. And we know the sigma square as an expected value of x minus mu, means that it will be equal to the expected value. It's a general formula for the function. It will be expected value of x minus mu of x square. So to calculate that one, we can simply use this formula to find the values, because the expected value of any function can be defined as summation of that function, means that it will be summation of x minus mu square times the function of the distribution times f of x, and f of x over here is given by 1 over k. So we just resulted to the following variances. So we can calculate the variance and the expected value for this case as follow. We will introduce the distribution first, and then we calculate their mu and also the sigma square by using that formula. So to understand the second type of the discrete distribution functions, we just prepare one type of the statistical experiment. We tossing the coin 3 times. So if we toss the coin 3 times, means that 3 times we flip that coin, and the result can be seen as one tree diagram that you can see over here. And this tree diagram can be listed the sample points in our sample space, or sample space is t, 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 h, and so on, based on a branch on this type of the tree diagram. I mean, in each branch we can have one element that I just determined it over here. So in this experiment, we have one important factor, that for each time of a tossing, we have two cases. Means that for the first one that we toss the coin, we have two cases, the head and tail. For the second one also we have head and tail. For the third one also we have tail and head. Means that over here we have some type of the binary operators. For each case that we have some statistical experiment, we have 3 times of some statistical experiment here. For each time of this statistical experiment, we have a head or tail, that the head is our concern and the tail is not our concern. So for the second one we have the same thing, and for the third one also we have the same things. And the probability during of this experiment is not changed. It's invariant from the first to the last. I mean, it's not changed. The probability of getting heads at the first one is half, at the second one is half, at the third one is half, and it's not changed. Moreover, X denotes the number of heads, the number of the things that is our concern. So based on the definition of X that denotes the number of heads, I can assign a numerical value for each sample points. Means that at the first one, for example, we have no heads, there is all tail, we have T, so the number of heads are 0. So we assign 0 for the first sample points. For the second one we have 1, for the third one we have 1, and so on. And based on these actually numbers, the number of actually the probability for each of them are as follow in that table. So as you can see over here, we have a probability distribution function, and we construct this probability distribution function based on information that we listed on above. So the question is about the finding this type of the properties generally for any experiment. Means that let us take a look again at the concept that we have it over here. We have one experiment that is repeated 3 times. Let me just put a number n as 3, means that this statistical experiment happened 3 times over here. Moreover, for each of these experiments we have 2 cases. One case is getting head, which is our concern, and one is getting tail, as is not our concern. And the probability of getting head over here is equal to half, which is our success, which is our concern over here. And our failure in that experiment is getting tail, which is equal to half. And this value is invariant, is constant, is persistent for all values inside of our statistical experiment. And of course we should have the probability of success, or that concern, plus the probability of failure equal to 1. And as you can see, we have this property over there. Means that for each time of experiment we have 2 cases, one success, one failure, and for the success and failure the addition of this probability is equal to 1. And more important thing is about the X, or the random variable over here. X denotes the number of the success, or the number of heads in our statistical experiment. So we construct this table, but is there another alternative way to calculate the probability or construct this distribution function without using that properties, without listing the sample points? If the number of the experiment is 100, then finding the sample spaces and sample points and count the number of the success is not that much easy. So what shall we do? First of all, we should see that how did we earn the number 3/8, for example, over there. So means that over here the probability of X equal to 1, or getting 1 head, means that we are looking for 1 head out of 3 cases that we have it. This 1 head can be appeared at the first, can be appeared at the second, or can be appeared at the third part of the actually queue or that group of elements or objects that we have it over there. So by the another words, we have the combination of 1 out of 3 as a cases that we can consider it over here. So by the another word, we can write that number as a 1 over 3. So this is the number of the cases that we can find. It means that the number of head can be found as a 1 case, which is the number of the success out of the whole possible cases that we have it, which is 3 cases. So 1 out of 3 over 8 is a probability that we have it. So by the another word also, we can calculate that one as follow. We can rewrite it as a 1 over 3 times 1 over 2 to the power of 3. So right now we can compare the probability of the success over here as well. So if you just take a look over here, we have this type of the solution for that one, and 1 over 3 of course is 3, and 1 over 2 cube is 8, so we have 3 over 8. Is it correct for calculating the probability of x equal to 2? Means that do we have the same formula for that one? For sure over here for probability of x equal to 2, we have 2 objects or 2 heads out of 3 experiment that we had it, so it will be 2 out of 3 over 8, and again we reach to 3 over 8 because 2 out of 3 is 3, so we have 3 out of 8, 3 over 8 for the case that the x is equal to 2. For 0 and 3 also we have the similar things. So let us take a look at one another example and see this similarity in that type of the experiment to just decide about the formula and general formula that we can reach from this discussions. So let us take a look at the next example and we try to recap our information about binomial distribution in this example, and at the end of the day we will find a general formula for that type of the distribution. In the question they mentioned that the probability that a patient recovers from a rare blood disease is 0.4. So diagnosing the disease is similar to diagnose the type of the distribution over here. By some type of the information that is given in the question, you can find the information of that distribution. So you should behave like a practitioner, like a doctor who diagnose the disease. Over here you should diagnose the type of the distribution instead of diagnosing the disease. So over here we have a patient that recovers from a rare blood disease, and the probability of this surviving this type of the salvation over here is 0.4. So for each person we have 2 conditions. Like a previous case, I try to find the similarity of this question and the previous one. Means that for each person we have 2 cases. 0.4 is a probability of surviving, means that 40% of them will be survived, and 0.6 will pass from this disease. So means that we have a probability of some concern. Our concern is over here is surviving. So the probability that we have it over here is 0.4, that we denoted by P, and the another probability of a failure that the person actually passed from a disease or cannot survive is given by Q, which is 0.6, and the addition of them is equal to 1. Up to this point of the question I just realized this information. In the next part they said that we have 15 people. So means that the number of the experiment that we want to talk about them is 15. So out of 15 person, if I just list that 15 person over here, let me just list them. So I list them over here, 15 people, and with the color red and blue, I determine the surviving and passing from that rare disease, rare blood disease. So over here, as you can see, they looks like a tail and heads that we list them over here. And over here at the end of the day, they ask you what is the probability that at least 2% survive, or between 3 or 7 survive, or exactly 5 survive. So means that if we want to calculate the probability, the most important thing is the surviving people. Means that over here we should talk about the number of a survivor out of this 15%. So for this reason we define the random variable x as the things that denotes the number of successes, and number of the successes over here is number of survivor. So because of that, we can consider the x as a number of the survivor. Right now we should know their distribution to talk about the probability of something. So over here, each part of that question determine the probability of x equal to something. Means that for instance, I'll just talk about the part B, that they discuss about the cases that is survived between 3 and 7, or the last part, exactly 5 survivor is us. So let us consider the last part of the question, that we want to know what is the probability of 5 survivor. Means that I'm looking for the probability that x, or number of the survivor, is equal to 5. Based on the information that we get it in the previous part, we can say that, okay, so that 5% that we talk about it has some numbers. Means that to count the number of 5 actually survivor out of 15 cases, I should use a combination of 5 out of 15. So it's important to understand that to calculate the number of the survivor, we can calculate this combination of 5 out of 15. This is the part C. Let us solve the part C first. So for the cases of 5 out of 15, we should divide them by the number of the probabilities. So if in a previous question we divide them by 8, 2 to the power of 3, or the probability of a success to the number of the successes over there. So because of that, we multiply this value by 0.4, which determine the probability of successes to the number of the success that we want it, which is 5. And to complete the conclusion, we should multiply by 0.6 the number of the failure to the power of number of the failure, which is 10. We have 10 failure over here. So means that we can reach to the formula, the general formula for that binomial distribution. So this is the form of a general formula. Means that the general binomial polynomial formula is as follow. We have the probability of case successes out of n. Where we have this type of the thing, we can say that the type of the distribution is binomial distribution. We have some diagnose character over here. First, for each of that type of the experiment, we have 2 cases. One of them is success with the probability of P, and the another one is a failure with the probability of Q. This P and Q is constant, is invariant for each of these experiments. It's not changed during of that statistical experiment. We have n type of the experiment that we have it, and x denotes the number of the successes. If all of this condition holds true, number of successes over there, so if all of this condition holds true, then we can say that the probability distribution of x is binomial, and we denote it like this. We said that x follow the binomial distribution with 2 factors. The factor is n, the number of the experiment, and p, which determine the probability of the success. So I just repeat it again. If we have n statistical experiment. If you have n statistical experiment, means that n times we just repeatedly do the same thing, and out of this n times, in each of this experiment we have two cases, one success, one failure, with the probability of p and probability of q. Of course, p plus q is equal to 1. And also these numbers are constant, it's not changed in the duration of this statistical experiment. And if x denotes the number of successes, then we can say that x follow the binomial distribution with the factor of n and p. So if this condition holds true and we found out that the x follow the binomial distribution with the factor of n and p, then the probability of x equal to k, or the probability of x equal to k, or getting k actually successes out of n cases, it's equal to this formula. This is the combination of k out of n. This is the probability of success to the number of the successes, and this is the probability of failure to the number of the failure, which is n minus k. Over here we did the same thing to calculate this formula, and simply you can calculate this one or leave it like that. So at the part, let us solve the part A and B at this question as well. At the part A at this question, they ask you that to have at least 2 survivor. So at least means that the minimum. We want to have more than that one. X at least means that it should be calculated for greater than 2. When we said that at least 2 means that we want to have more than 2. If in the question they mention that included 2, then you should put the equality. Otherwise, you just leave it with the inequality. I just mentioned it again that if in the question it's not mentioned about the inclusion of that number, we exclude that number and just put the inequality without putting the equality at the bottom. So I'm looking for the probability of x equal to x greater than 2. When I just talk about the probability of x greater than 2, it contains the probability of x equal to 3, x equal to 4, x equal to 5, x equal to 6, and so on. Means that it started from 3 up to 15. But calculating all of them and add them together, it's not that much easy. For this reason, I just use the complementary part instead of direct calculation of 15 cases that we have it over there. Means that I know the total cases, the total probability should be equal to 1. So I subtract the probability of x equal to 0 and x equal to 1 and x equal to 2 from that case to calculate the whole probability. Means that you can also calculate the probability of x equal to 3 up to 15, but instead of that one I calculate only 3 values and I subtract that 3 values from 1 to calculate the remaining parts. So if I subtract that one, then I can calculate the probability of x greater than 2, and let us calculate them and write it over here. Probability of x equal to 0 means that I'm looking for 0 success out of 15 cases, so it's a combination of 0 out of 15. The probability of p, which is 0.4 to the power of 0, times the probability of failure to the number of failure. The probability of failure is 0.6, and I just write the exponent as 15. For the case that we have the probability of x equal to 1, I will write it as a combination of 1 out of 15. Right now the probability of the success, which is 0.4 to the power of 1 times the probability of failure, which is 0.6 to the power of number of failure, and the number of the failure over here is 14. And for the last one as well, we have the same thing. Again, we have 2 successes out of 15 cases or 15 statistical experiment, 2 out of n. And then the probability of the success 0.4 to the power of the number of successes, which is 2, times the probability of failure 0.6 to the power of number of failure, and number of failure over here is 13. So this is gonna be the part B, part A. And for the part B, that they ask you to find the probability of the cases that we have between 3 and 7 survivor. Again, we have the similar situation over here. Let me just erase this part, and then let me just keep it because we want to talk about it more as well. So at the part B, as I said it, again, I want to emphasize about the inclusion over here. When we said that the probability of being survived between 3 and 7, then 3 and 7 will not be included in that value. If in a question the inclusion is mentioned, then you should consider the inclusion as well. So x between 3 and 7 means that it contains the probability of x equal to 4, x equal to 5, and x equal to 6. So it's gonna be the addition of all these probabilities, and again we should add all of them with the same formula. So it's not a bad idea to repeat it for yourself, then you can keep it in your mind and memorize it. It's necessary to memorize this formula at the end. So the probability of x equal to 4 means that 4 successes out of 15 cases that we have it, and multiplied by the probability of success, which is 0.4 to the power of 4, which is the number of the success that we look for, and the probability of failure is 0.6 to the number of the failure, which is 15 minus 4 or 11 failure, and it should be calculated up to the case that we have the probability of x equal to 6, and again we have 6 successes out of 15 cases, and the probability of the success is 0.4 to the power of 6, 0.4 to the power of 6, and the probability of failure is 0.6 to the power of 9, which is a number of the failure on that case. So we could solve that question by recapping all of that information about the binomial distribution. I just recall that one, that for the mean value of these things, the mu is equal to np, and the variances or sigma square is equal to npq, or np times 1 minus p. But how could we reach to that formula? Most of the time, in the time that I gave that course, I just asked the student to find that one as a bonus, and they found the formula for that cases. But I just want to give you the insight of that one without solving the that type of the question. Of course, the expected value was calculated as a multiplication of xi, the random variable that we have it, the xi, the random variable that we have it, by the probability distribution function. Means that it should be calculate this one to find the expected value. This is the general formula for the expected value. At this case, we have indeed the I between 0 up to n cases, because we have the 0 successes out to the n successes out of n statistical experiment, and xi over here can be considered as a number of I is a number of the successes that should be multiplied by the probability of I, and the probability of I will be I out of n, the probability of the success p to the power of I, and the probability of a failure means that q to the power of n minus I. So by some simple techniques you can find after some steps, means that you need some step in the middle over here to reach to the formula of n times p. I mean, it's not that much difficult, but it needs some techniques of the calculation for the summation formula. So I hope that you can find the result of that one and find the formula, you know, that way. But if you have some problem, you can write comments, and I will give you the formula at the comments as well. So let us take a look at some more examples and solve that one as well. Let us take a look at another example for that type of the things. Over here I want to mention something, because our discussion is about the binomial distribution. Diagnosing the question and the method of the solution is easy, but you should care about these things, that in an exam or any type of the real application for that type of the things, the distribution is not given at the beginning, then you will solve some example. You should prepare yourself by some method to diagnose the type of the distribution. Otherwise you cannot solve the question, or wrongly you just use the wrong method of the solution. At the end of the day, when we discuss about all type of the distribution, we will discuss about some question that cover all type of the distribution, and based on that type of the things we will discuss about the differences between these distributions, and we will solve it with the different distributions. So let us take a look at this example. One prominent physician claims that 70% of those who with lung cancers are heavily smokers. Means that out of the people who got the lung cancer, 70% of them are smokers, 30% are not. If his assertion is correct, find the probability that out of 10 such a patient recently admitted to a hospital, more than half are heavy smokers, and so on. So first of all, for any patient that we consider, it's assume that it's a person who is patient, then we have two conditions for that person. Means that one condition that the person is a smoker. So let me just sketch the cigarette over here, and one person who is not smoker. So if you got that patient and you are not smoker, then this probability is 0.3 based on the assertion or this claim of that physician, and 0.7 is a probability of being a smoker if you are a patient, if you are a patient and you got that lung cancer. So we examine 10%, means that the n or the number of the people who examines are 10, and over here if x denotes the number of smoker, so I should mention it over here, x denotes the numbers of smokers out of this actually people that we examine, out of these people who got the cancer, then we talk about the probability of x. Right now all conditions for the binomial distribution holds true over here. First, for each person that we consider, there is two cases, 0.7 being a smoker and 0.3 is not being a smoker, and this probability based on that information is constant. Means that for each person we have the same thing, and means that we have a success and failure, and the addition of them is equal to 1. We have 10 statistical experiments, and more of that, the x denotes the number of success or being a smoker. So right now for the first part, more than half are heavy smokers. Means that at the part A I'm looking for the probability of x greater than half of 10%, means that greater than 5. So it will be equal to the probability of x equal to 6 up to probability of x equal to 10. I should calculate that probabilities to find the probability of at least half of them will be a smoker, or more than half will be a smoker. So I should add these probabilities to calculate, to evaluate that probability as well. So to calculate that probability, I should evaluate these values. So the first one is a 6 cases out of 10 people that we have it, and the probability of success means that 0.7 to the power of number of the success over here, which is 6, and the probability of failure, which is 0.3 to the power of number of failure over here, which is 4 cases, and it should go on up to the end to calculate the last probability, which is 10 out of 10. The probability that we have it 10 cases out of 10. The probability of success over here is 0.7 to the power of number of the successes over here, which is 10, 0.3 to the power of 0, because we have no failure at the last case. So this is the actually part 1. The part 2 asks you to find exactly 4 are heavily smoker, so means that I'm looking for the probability of x equal to 4, and the probability of x equal to 4 based on that distribution function is 4 out of 10. Then the probability of success, or 0.7 to the power of 4, and the probability of failure means 0.3 to the power of the remains part, which is 6. And of course you know how to calculate that combination. The combination of 10 over 4 will be 10 times 9 times 8 times 7. So we just select 4 cases over there, because it will be actually cancelled by the 6 factorial at the denominator, and at the denominator we have 4 times 3 times 2 times 1. It's no need to write 1 as well. So this will be the value for that combination. I just mentioned the value for the combination, and the remaining parts are the same, so you should write it there. For the part C as well, we have less than 2 are non-smoker. Less than 2 means that 2 is not included in the question, it's not mentioned. So x less than 2 means that 0 and 1 should be considered as a cases that we have it. Probability of x equal to 0, non-smoker will be between them, and the probability of x equal to 1 should be put it over there. So probability of x equal to 1, and to calculate that one you should use a formula again. So it will be 0 out of 10, 0 out of 10, and the probability of success, which is 0.7 to the power of success, which is 0, and probability of failure, which is 0.3 to the power of number of the failure over there, which is 10. And for the case 1, again we have the same formula, means that we have 1 out of 10 right now, because we are looking for 1 success out of 10 cases. Then we should multiply it by the probability of success over here, which is 0.7 to the power of 1, and 0.3 to the power of remained part, which is 9. So this will be the case that we have it over here. So in the next example we have this question that the x follow the binomial distribution. At this question you don't need to diagnose the type of the distribution, just we know that the x follow the binomial distribution, but the number of the statistical experiment over here n, and the probability of p or the success is not given. Instead of that one we have 2 information. One is expected value. The expected value, or the mu, is given as a 20 over 3, and also the variances of that one is given by 40 over 9, means that the sigma square over here is 40 over 9. But we know some relation of actually expected value and variances. We know that the mu can be calculated as np, and the sigma square, or the variances, can be calculated as a npq. Right now, by dividing these things we can find the q, means that q over here is equal to npq over np, or sigma square over mu. So by calculating that one we can find the mu as well, and sigma square is given by 40 over 9. Let me just write it here, 40 over 9, and the mu over there is given by 20 over 3. So if I just write over there the value that we have it, so 40 by 20 will be cancelled, we have 2, and this 9 is coming to the denominator, 3 to the numerator, so we have 2 over 3 at the end of the day. So this is q. Then when we have a q we can find p as well. P will be equal to 1 minus q, So 1 minus 2 over 3 is equal to 1 over 3. We have 1 over 3 as a p, and right now we have np as well. np is given as 20 over 3, so means that n over 3 is equal to 20 over 3. So right now we can find the number of n as well, because np is given here, 20 over 3, so n is equal to 20. Right now, by knowing this information, everything is clear for that type of the distribution, and we can calculate the probability of x equal to 3 as well. So the probability of x equal to 3 right now will be the combination of 3 out of 20, 23 chosen indeed, times the probability of success over here, which is 1 over 3 to the power of 3, number of the success, and the probability of failure, which is 2 over 3 to the power of remains. 20 minus 3 is 17, so it will be the value for that case. So I just finished our lecture by solving that example, and in the next lecture we will discuss about the remaining parts of the discrete distribution. Thank you for your attention.